Lisaslaidid. Sul on Kai omadele vastusid siin? No osadele asjadele.
Ma annan mikrofoni, aga praegu ma lülitan ise mikrofoni siis sisse.
Mina ka. So, tere hommikut. Good morning, ladies and gentlemen, and I'm pleased to open this defense ceremony. And we have Kaur Tuttelberg, our PhD student, who is going to make his defense on the topic continuous monitoring of power system inertia and transmission loss components using synchronized phasor measurements. My name is Ivo Palu. I'm a professor, head of department and chairman of this defense committee. We have gathered all the documents that are needed to proceed. I'm quickly flipping through the documents. So we have Dean's order that of the committee. We have committee members, me, then Hannes Agabus, then Mart Landsberg, Mati Meldorf, Toomas Rang. We have a missing person, Toomas Rauhala. He is not able to join us. Then we have Indrek Raasto and two opponents who are also part of the Defense Committee, Kai Struns, who is present. Welcome. And Vladimir Derzia, who should be online over the Skype. We can see you. Hope you can see us. Yes, we have a PhD student as well. So we have covered this. Then we have voting tickets we need to have later on. We have a written decision from Kaur's supervisor, Jaako Kilter, who is also here. Then we have written opinions from the opponents in case something happens with telecommunication or for just the bureaucracy. We have to have these statements afterwards as well. Then we have the review of the theses made before the opponents. We have the plagiarism report, which states that there are some overlapping, but nothing to be worried, because these are basically the correspondence to our own documents. And what we are missing is the defense speech, discussion, voting, and hopefully celebrating. So, but to proceed, then, as I heard, you have made the slides, and you will cover roughly 30 minutes. After that, we will have the opponent questions. Is it okay if we start with Kai, who is here? Vladimir, is it okay? Yes, the second one. And then the key goes to the Defense Committee and then to the audience. Then we have a little word from supervisor and then voting. And these are the procedures. So the floor is yours, please.
Thank you. Dear members of the committee and the audience, I am Kaur Tuttelberg, and I would like to present the main findings of my PhD thesis. In the presentation, I will first introduce the challenges the thesis tackled, followed by an overview of the monitoring technology that the applications are based on. I will briefly discuss transmission losses and the components of transmission losses. Following that, I will introduce the method of monitoring these transmission loss components. Then I will briefly go over the basics of frequency control in power systems and the role of inertia. Following that, I will introduce the measurement-based method for continuous monitoring of inertia. Transmission losses are one of the responsibilities of a transmission system operator. The TSO has to cover the energy consumed as losses in the transmission network. And in order to do that, transmission losses are forecast so that they can be procured. However, corona losses can be quite difficult to forecast, which is partly due to the fact that not a lot of monitoring data has been available. Another concern in power systems is maintaining frequency close to its nominal value. However, with increasing share of renewable energy sources coupled through power electronics, inertia has decreased in some power systems, which has introduced problems with maintaining frequency stability, and in the future might hinder further integration of renewable sources. And so far, measurement-based methods for continuously monitoring inertia have not been available. As we're discussing monitoring applications, I will quickly go over the technology. Conventionally, power systems have been monitored using SCADA and energy management systems. These systems gather measurement data from across the system with a rate of a few seconds or tens of seconds. The measurement data is not time synchronized, and it enables the power system to be observed as if it was in steady state. However, in the past decade, synchronized phasor measurements have become more widespread. These measurement devices measure time-synchronized phasors at reporting rates in the order of tens of milliseconds. And this enables dynamic phenomena in the system to be observed and monitored. As the name implies, phasor measurement units measure both amplitudes and angles of current and voltage phasors. In addition to that, they measure frequency and the rate of change of frequency. The measurement data is time synchronized and reported to a central wide area monitoring system. Here we can see an example of a PMU connected to a transmission line feeder, where we have a time source and current and voltage signals from the current and voltage transformers. Most of the transmission losses in a transmission network are due to Joule heating. In the photo on the left, we can see an overloaded distribution line glowing red with the heat. And in the other photo, we can see the glow of corona discharge on a transmission line. Even though most of the transmission losses are due to Joule heating, in certain conditions, corona losses can be quite significant and even larger than Joule losses. I'm afraid I can't switch to the next slide now. Okay. When analyzing a transmission line, we can use a model or an equivalent circuit. And in the equivalent circuit of a transmission line, we can model the Joule losses in the resistance of the conductor, and we can model corona losses in shunt conductance. However, corona losses can be quite difficult to determine. Let's see. Yeah, I can't switch the slide. Okay. Traditionally, corona losses have been measured in dedicated experiments where special measurement equipment has been used. And from these experimental measurements, empirical equations have been derived. However, these can be quite difficult to transfer from case to case and are difficult and expensive to carry out for each line. You can see one of the examples of these empirical equations, where we have the dependence on electric field intensity, but also a coefficient dependent both on weather conditions and properties of the conductor surface. And these can be quite difficult to determine on an operating transmission line. To illustrate the dependence on various quantities, we can take a look at the results from a previous study carried out in Sweden with a dedicated measurement setup, including calibrated instrument transformers. We can see the dependence of corona losses on average conductor temperature and relative humidity, and also average wind velocity and phase voltage. In the thesis, I propose to use PMU measurements in order to calculate transmission losses as components. The main hypothesis is that PMUs enable the transmission line to be monitored in more detail so that these components of losses can be calculated directly. In order to do that, I have derived the necessary equations and analyzed uncertainty propagation in the monitoring application. I have tested the method on real measurement data and validated the results of monitoring corona losses based on analyzing the same dependencies we saw in the previous figures and comparing these dependencies. I can't switch the slides for a minute again. Thanks. So as I said, the main principle is that with PMUs, we can monitor the transmission line in more detail. We can obtain phasors measured at both ends of the transmission line from one time instance. And based on that and the transmission line model, we can derive components of transmission losses that correspond to Chow losses and corona losses. However, in the measurements, we have some uncertainties. And in case of phasors, we have an uncertainty both in the amplitude and in the phase angle. And these are not necessarily equal. So in order to analyze uncertainty propagation, I have applied the principles of analyzing uncertainties in two-dimensional or complex quantities. And I have tested the method on measurement data from two transmission lines in the Estonian power system. In addition to the measured transmission loss components, I have gathered weather monitoring data from weather stations in the vicinity of the transmission lines. I have used a bit more than 4 months of monitoring data in the study, where we can see varying weather conditions from wintry to summery. And based on the available information about the measurement devices, I have analyzed uncertainties in the results. Here we can see an example where I have calculated the total losses, Chow losses, and corona losses, and their uncertainty intervals. One important thing to note here is that in some cases we can see these small negative values in corona losses, which is mostly due to the systematic errors from the measurement devices propagated into the estimates of corona losses. So when we're applying it on transmission line, we have to fix this systematic error or bias. Now we can take a look at longer term monitoring data, where we can see the measured corona losses and their dependence on the same quantities we observed earlier. So dependence on average conductor temperature and relative humidity, and also dependence on average wind velocity and phase voltage. So we can see that in general the dependence of corona losses on these quantities is similar to what we saw from the previously published study. In conclusion, I have developed and presented a method to calculate Joule losses and corona losses as separate components using PMU measurements. The results of monitoring corona losses have validated based on this comparison of the dependence of corona losses on these weather parameters. We can monitor corona losses over longer periods of time and detect events when significant corona losses are present. This is a necessary input to obtain forecast models that enable corona losses to be forecasted and possibly reduce the expenses on loss energy imbalance. Following from here, I would introduce the second monitoring application and firstly start from a quick overview of the basics of frequency control. So in the case of a sudden imbalance in load and generation in a power system, the synchronous generators start either to accelerate or decelerate. At the first instance of that, the inertia of the generators stops the limits the change in frequency. And here we can see the inertial response. After the frequency has deviated from the rated value, droop control is actuated, which limits the or stops the frequency excursion. And later on, secondary control returns frequency to its nominal value. And in the following, I will concentrate on the inertial response part. Conventionally, in power systems, frequency has been determined by the synchronous speed of generators. Frequency is maintained with the help of frequency control, and it is dependent on maintaining the balance of load and generation. The generators and turbines have large spinning masses, which at the instance of a power mismatch limit the first change in frequency. However, with an increasing share of renewable sources coupled through power electronics, inertia has decreased in some systems. At this first time instance, when we have the power imbalance, we can model using the swing equation. And this tells us what the rate of change of frequency is for a disturbance of a given size. This inertial response in the power system is in principle present after any load variation in the system. However, with small variations, it is normally not distinguishable in the measured frequency. However, in case of large disturbances, it can be clearly seen, and so far measurement-based methods of estimating inertia have relied on such disturbances. Another aspect I have discussed in the thesis is that the inertial response of the power system is not determined only by the inertia of the rotating generators. But there are other effects in the system, like voltage and frequency dependence of load, that behave similarly and together provide an effective inertial response. So what the monitoring method that I'm proposing is estimating is this effective inertial response of the system. As I mentioned, conventionally, inertia from measurements has been estimated using significant disturbances. Here is an example where a large industrial load has tripped, causing a significant frequency excursion. However, I have proposed that we can use small load variations in normal operating conditions and the corresponding frequency deviations to infer the value of inertia. I have hypothesized that if we monitor these small variations for a sufficiently long period, we can infer some dynamic properties of the system from this measurement data. In order to do that, I have proposed a way to approximate the load variations and to use these and frequency variations to identify black box models to fit these dynamics. From these models, it is possible to extract the inertial response and the value of inertia. And based on that, we can determine the rate of change of frequency for a disturbance of a given size. And based on measurement data from a real power system, I have tested and validated this method. In order to introduce the basics of the method, we can look at the simplified model of frequency control in a two-area power system. We can see the troop control loops and boundary power flow between the areas. But in this method, we assume the approximated load variations and frequency deviations as inputs and outputs and fit the black box model to these dynamics. I have tested this method on measurement data from the Icelandic power system, where I have estimated the inertia of two areas of the system and the entire system. 16 disturbances, either trips of large loads or generators, have been used for validation. I have estimated the inertia values from measurement data before these disturbances, and then used the disturbances to validate the results by comparing the ROC-off predicted from the inertia value to the actual ROC-off recorded in the event. Here is an example of the data used in the application, where we see the approximated load variations in the two areas and corresponding frequency changes. In total, approximately 30 minutes of monitoring data is gathered for these estimates. I have analyzed the events in detail, where I have compared the responses of the identified models to the response of the system, and compared the rate of change of frequency values predicted and seen in the events. In conclusion, I have demonstrated that we can estimate inertia based on measurement data in a continuous manner. The ambient measurement data used in the application includes enough information that we can estimate some dynamic properties of the power system. With this, it is possible to have a current value of effective inertia that is known to either the operator or control systems. We can know what the rate of change of frequency would be for a given disturbance, for example, a trip of the largest unit. And it can enable new applications of fast frequency control. And to summarize my work presented in the thesis, I have developed and presented a method for monitoring Joule and corona losses as separate components, analyzed the uncertainty propagation in this monitoring application, and presented a measurement-based method for continuously monitoring inertia in power systems. These and associated results have been presented in these publications. In the future, I would like to continue this work in several aspects. We can analyze corona losses across a system, that means over several transmission lines. Also compare corona losses on different lines. And develop, using long-term monitoring data, develop forecast models. Also to test the applicability of identifying inertia in different kinds of power systems and parts of larger systems. And study the applicability of similar methods in identifying other dynamic properties of power systems. I would like to thank the two TSOs who enabled me to test these methods, Landsnet and Elering. I would like to thank my colleagues from the Migrate project, the Archimedes Foundation that has supported me during the PhD studies, NTNU, who hosted me for a research day, and all of my colleagues. And that is all from me. Thank you.
Thank you. So, thank you for the presentation. Nicely in time and exceeding it, which gives us some extra minutes for questions. This is always welcome. We will move on to components. So, Kai, we will start with you.
Okay.
So the mics on the table should be able to catch you, so you can just speak normally. You don't have to take it hand. So please, Kai.
So thank you very much for the presentation. Of course, I did not only look at the presentation, I also read your thesis document, which I found well explained. And also I found that that it's very good you made the next step in modeling, which is maybe not so evident from what you presented here, but for example, you mentioned that there are these empirical old formulas on corona, and you basically went down to the physics and redid the whole work and combined it with modern measurement techniques and find, okay, where is the next step in getting these models right? This is, I think, what was very good. And I also liked very much in your thesis document that you also had a lot of critical assessment of the results, okay, which I found you maybe also due to the lack of time, you did not stress so much here in the presentation. But I think those critical assessments are actually one of the most interesting parts, because okay, we may think PMUs is very accurate and opens a lot of stores, and they surely do, for sure. But you know, as you have shown, I mean, not everything is accurate at the first attempt of the modeling. So that was very, very good. And I think you could have stressed that a little bit more in the presentation, but we can do that through the discussion. So, for example, one item I'd like to come back to was your picture, your figure with the corona losses, the example. Can you show it to us?
The photo?
Not the photo, but your graph.
The graphs,
your
okay.
graph with the
so,
measure.
Yes. Just a second.
I think it was slide 15. Slide 15. Okay.
This one.
Yeah.
Yes.
So first, I mean, at your introductory slide, you said SCADA, EMS, and so on. So based from the control system perspective, from the control center perspective, are the people sitting in the control center and they say, oh, what was missing are the corona losses? We need to have them? Or can you explain why the motivation was to look specifically in the context of SCADA, EMS, and control centers?
Well, I don't think it is that much of a concern for an operator in a control room that much. But as I mentioned, it is more of a concern of cost, as the loss energy is procured on the energy market, and if the forecast is not correct, there is extra expense on the loss energy imbalance. So this is more of a question of then being able to obtain information about corona losses over periods of time, to know in which conditions they are present and significant, and then be able to forecast these situations better.
What kind of situations?
Well, these situations when corona losses are significant.
Okay, when corona losses are significant. So if you look at the results now of these corona losses, and I know it's hard to validate, but you found some correlation with temperatures that don't go in the right direction. And as you said, also it goes into negative, okay? It goes into negative not for a short moment, for a long time. So what does it mean?
Well, as I discussed during the presentation, it is basically caused by systematic measurement errors in the measurement devices. That is, for example, current and voltage transformers, as they have certain errors in the measurements. And as we did not have calibrated instrument transformers available, there are some systematic errors in the measurement data. And I have another slide, just even in the experiment I referred to from Sweden, where they did indeed have calibrated instrument transformers, we can still see occasions when they evaluate corona losses with negative values. And so there are, of course, some limits to the accuracy of the measurement data, and this has to be considered.
So when you looked at the further work, okay, you suggested as further work we monitor more lines on corona losses. What would be the suggestion of further work, first getting rid of the error before we monitor more lines with negative losses?
Well, of course, it would be good to be able to calibrate all of the measurement devices and obtain better accuracy from there. We can also use some statistical analysis to at least correct a part of the systematic error.
Well, I think that's the key word that you mentioned. Also, I think you mentioned it during the presentation. You said the systematic error. So shouldn't it be
It
possible?
it is quite constant over time. Not exactly, but quite.
Yeah, but
quite steady
exactly,
over time.
yeah, that's what you see. It's constant over time mostly. So shouldn't it be possible to find out what the systematic error is and then somehow
Yes.
introduce an offset and say,
Yes, basically that's what has to be done, and if we go back to these results here, these offset or bias has been fixed based on a statistical analysis of the measurement data, which in further work hopefully I will be able to present in more detail. So I suppose this should have been in the list of further work as well.
okay, let's go back to the 15. It's just one slide
Yes.
forward, which is of course a very, very good picture. So it was based on a comprehensive physical modeling of the whole transmission line that was included for the joule losses, as you name it, and the corona losses. So it's on one side of the transmission line and the other side of the transmission line. What if you look at it as input and output and say, okay, power injected on one side of the transmission line and taking power out at the other side of the transmission line, and then measuring it accurately on both sides? Is that a means of validating that pictures and finding out those components as an alternative?
Well, if I understand correctly, this is in principle how transmission losses are measured,
Right.
as they are now, and this is the black line basically.
That's the black line. Okay, so that's the.
And yes.
So the black line is not the blue plus the red one, but
It is. It is the total losses, which consist of the sum of these two.
okay. But you can do that also without having a line model. Okay, just measuring the power on one side and on the other side of the line.
Yes, but that way you can get the black line, but not the other two.
Right. Okay.
Well, in some cases, what is done is that well, the total losses are measured, and then the joule losses are approximated based on measured current and a known resistance, and then corona losses are evaluated as the difference. But as we can also see here, we can obtain significantly smaller uncertainty interval if we measure corona losses as a separate component from these synchronized phasors measured from both ends. Because if we apply the other approach, we have to consider these large uncertainty intervals.
Okay, let's move for a moment to the inertia.
Yes.
Which is, of course, a very topic of coming interest. And you selected the country of Iceland, which is an island. And your key innovation, as you said, is that you just use it from basically ambient noise, okay, normal load changes and what they do to the frequency. And the frequency has quite some excursions in Iceland, okay, much more, for example, as we have it here in the continental system. So saying that here in the continental system our ambient frequency variations are much smaller compared with that. So the question is then, what was said to be the biggest advantage works, of course, well for the Iceland system, but will it still be working here?
It's a good question, of course. Well, I think there are two aspects here. In principle, this is based on assuming that these dynamics are linear, so that it is not really necessary how small the variations are. But of course, then there is a question of detecting and measuring these changes correctly. And I have not had an opportunity to test the method on the system of continental Europe, for example. However, after completing the PhD thesis, I did carry out a small test on the example of Scotland in the power system of Great Britain, which is larger and has smaller variations, and we can see some of the results from there, where the estimates of inertia obtained with this method are compared to event-based estimates. There are some limitations here, as there were fewer measurement points available and the quality of measurement signals was not as good, but in general the test showed that the method is still applicable also in a case like that, where a smaller part of a larger system was monitored. The part of Scotland in the power system of Great Britain. So it is still not a very large system, but it's larger than Iceland.
Mm-hmm, mm-hmm. What's the accuracy target? So you can say it's a good estimate.
Well, it's a good question, and I suppose it depends on the application, but I would say if the error is maybe between 10 and 20%, it should still be acceptable, as it is a more or less a continuous estimate, and it varies over time.
Okay.
But I suppose this is a question to those who apply these results.
Okay.
Can't say for sure.
Okay. I'd like to pass the word to my other opponent colleague for a while.
Well, firstly, I would like to double check if you can hear me well.
Almost. I think I can understand.
I mean, I have also with some delay YouTube channel, but it is some 50 seconds to 30 days. But I would say that the communication infrastructure is acceptable. I would like to double check if the audience can hear me.
Well, we can't really hear you very well. It's chopping.
You know, can we retry this call? If you call me again, I believe that it might be better.
Yes,
okay?
Without video.
Yes, please try it without video, please. So, how is now? I would like to know.
It's better.
Good. Well, firstly, my apologies for not being available to be in Tallinn today. My apologies to you and now attending defense. Calling from China, and firstly was very pleased reading your PhD thesis, which has interestingly two very different topics. One topic has to do with corona, which has to do with electromagnetic fields, very different mathematical model. On the other hand, to work on slow electromechanical transient processes, which have to do with system inertia. I like the part in which you worked on uncertainty propagation, and what is then further seen in your work related to corona and true losses estimation. So, in your uncertainty assessment, is it my correct understanding that you have overtaken the existing methodology from the past? It is, I think, the old school, or?
Yes, this methodology has been published, and yes, I have used that.
Yes, well, this is traditionally very good. So interestingly, when reading your thesis, I asked myself, where did you define what uncertainty is? And because you're analyzing covariance matrix, so you are dealing with stochastic processes and random variables. This is a quite topic, very important topics. In this covariance matrix, traditionally talk about the expectation of something. So can you just give us a few words about what uncertainty definition is, please?
Well, in my own words, I would say uncertainty is, let's say, a range in the results that measurement data does not explain exactly.
Yes, this is one of nice description. When we have a measurement, for example, at instrument's former side, we have then that what we measure plus some noise.
Yes.
So that noise is traditionally introduced in this whole story, and then we discuss what is the noise model, and we are trying to find out the way, what is the progression of this noise through the whole chain of important components like instrument transform, phasor measurement unit, which is also a source of errors. You have numerical algorithms with the accuracy. Furthermore, communication channel, data concentrate, and GPS synchronization. So that I would mostly not missing this part, which, although I gave these comments in my independent report, in which I asked that you more specifically define what certainty is, because I believe that according to the definition of covariance matrix, it should be mathematical expectation. But I think that this is now something we could address maybe later in peace, but not now maybe in front of the audience. However, I really like the way how you implement the existing methodology for estimation of line parameters. So that is done very well, and then you have expanded that further to losses estimation. So is my understanding correct?
Yes, and I would give a brief comment about what you said earlier. In uncertainty analysis, usually two components are considered, where one treats the random errors or the noise, and another component that treats, well, that is used to include, for example, these systematic errors. And then these are combined. And also in this analysis, I have combined these, but the uncertainties from the noise are orders of magnitude smaller than the uncertainties from systematic errors. So this may confuse this analysis somewhat, so that it is more applied to propagation of these systematic errors. And also in metrology practice, it would be assumed that the systematic errors can be mostly determined and corrected in the results. But as the information about the measurement devices that was available was very limited, then I have assumed these systematic errors in the analysis of uncertainty propagation. So I hope this explains it a little bit.
Yes, thank you, Kaur. So I had some doubts, particularly when I looked at this graph given in slide 15, in which we had some negative values. Then I was concerned if really phasor measurement units are the appropriate infrastructure for monitoring precisely power system losses, because we see that the level of uncertainty is huge, and we move to negative values, which are, we have already observed that Professor Sturms has already raised this question, what was also my idea, but we have already enough elaborated that. Can you just tell us, firstly, I like that you use literature from 1912. I mean, very early work and results from last century, beginning of last century. How power system costs are precisely measured, or if they are at all precisely measured today? Can you just give us just a quick brief about it?
Well, one thing that I can add is that the measurement channels that are used in metering, where they measure losses, are let's say set up to be more accurate than the measurement channels for PMUs. At least that is something that I have been told.
Because, phasor measurement units are very appropriate for electromechanical type processes, but also from the perspective of the contributions of thesis, you have demonstrated quite nicely, precisely in a novel manner, how uncertainty propagation can be considered, assessed, and applied in one specific application, which was power system loss assessment. So this, from my perspective, is the contribution. Another question is, if PMUs are really the sensors which should be used for such a very complicated, very fine measurement of corona, because it's very, very small values, they're complicated to be measured, I would say. So anyway, I'm quite satisfied with this part, and if you allow me, I would like to move forward to chapter 4, in which you talked about inertia estimation. Okay?
Yes.
Good. So in this part, you are using swing equation, which is describing dynamics of the generator. And in this swing equation, what is dominating? It's something what is h, what is called inertia constant, and it is measured in seconds. Okay?
Yes.
Good. Can you please tell the audience and me, when you say power system inertia, what do you mean?
Well, in the thesis and this method of estimating inertia, what I mean is what I mean by inertia
how do you define
is
inertia?
it is the proportionality between rate of change of frequency and the size of the disturbance.
Yes, I saw this is this constant m, like Marta.
Yes, exactly.
All right, so, well, you know, when you talk to people from utilities, when you ask them what is system inertia, they talk about kinetic energy.
Yes.
So, and kinetic energy is calculated in gigawatt or gigavolt ampere second.
That's true.
But you have second square.
Yes, but I am estimating effective inertia, which is defined slightly differently. But I would say the idea of estimating it is still the same, to be able to tell what the rate of change of frequency would be for a given disturbance, for example.
Good. So you see, I asked you the question, what is inertia? But then you said effective inertia. I mean, it's such an important point that you precisely define to the audience. So I'm talking about effective inertia. It is obvious from your document, but it's probably not loud enough explained. Because this effective inertia, you have already mentioned, it is a consequence of firstly ordinary rotation and natural rotation of masses, and and we have something what is called the moment of inertia. It is traditionally described as a J. So this is contributing to this inertia. You agree?
Yes, I agree.
We have also demand side. Load is also contributing to its inertia.
Yes.
Now, what is also contributing to this inertia in this modern era today?
Sorry, was that the question?
So the question, what is also contributing today? We have some mechanisms, particularly on wind farms. What is contributing to this effective inertia? So
I'm not.
Well, you know, something like synthetic inertia.
Okay. Yes. Synthetic inertia.
Can you please give us a few comments about that? Because you nicely mentioned rotational inertia, you mentioned impact of load, and I was honestly a little bit missing this synthetic inertia, which is also making an impact of this delta P.
Yes. Well, synthetic inertia is somewhat different in the sense that, at least in most cases, it is measurement-based, so that the system that is providing synthetic inertia first has to measure frequency or rate of change of frequency, and then based on that actuate the control. So it is not instantaneous like the effective inertial response. So it acts with some sort of a delay.
Good. So anyway, you have already enough information in your thesis, and definitely I would like eventually that you put in your future work as one of items assessment of synthetic inertia in the scope of your effective inertia. So then we will have, I think, maybe a complete story if you mention this.
Yes, this is a good suggestion.
Good. All right. Thank you very much for accepting this. I'd like to finally just mention one point that from the perspective of inertia monitoring, that one of the issues is measurement of rate of frequency change. This variable is quite complicated to measure, to be measured precisely and without long time delays, something like 100 milliseconds, what is not nice. Do you have any comment on this, please?
Yes, this is a very good comment. I'll just switch to a slide to discuss this. And also in the validation of results, this was a problem in certain cases, because if we look at the frequency measured in the Icelandic system, which is very small, we can see that this linear change in frequency can be very short. And in certain cases, it was very difficult to calculate it. And in the validation, I specified that rate of change of frequency is calculated between 0.2 and 0.4 seconds. And even then, in some of the events, the change in frequency was not linear there, and already there were some problems with the comparison.
Mm-hmm. Yes. Well, good. Thank you very much for your answers. I would like now to give a word to the moderator of the session, please.
I think Kai will continue his questions. And we are coming back to you, so if you have any further questions.
Fine.
I'm referring to the document, okay? There are equations 217 to 18 that discover confidence levels, coverage factors, and I found them interesting, but like you to put them into context here, because you mainly draw them from a reference, okay? You said that the coverage factors for two-dimensional quantities are discussed in reference so-and-so. I'd like to tell us, explain with your own words about how you use them, okay? Because it seems like confidence levels, P and so on, there is some flexibility on how you choose them. Seems like, okay, but
Well,
so can you explain us how to get them? Maybe even with a, with a completely different example that's not related to transmission lines, something that is illustrative.
Well, when it comes to the confidence level, then it is usually selected when the experiment is carried out, depending on what level of confidence is desirable. So this is something that is selected for the experiment. And the coverage factors are then these scaling factors that are used to scale the standard uncertainty For example, in a case it could be basically standard deviation, and then for a confidence interval, then it is scaled by the coverage factor to obtain this level of confidence. And this difference in the 1 and 2 dimensional coverage factors, I have borrowed this example from the same report that I based a lot of this analysis on, where it is just illustrated that is in the 2-dimensional case it scales the area instead of like an interval on a single dimension.
So these confidence intervals are related to standard deviation?
Well, yes, but not only. I mean, it's because if let's say if uncertainty propagation is analyzed, then we combine different like these types or components of uncertainties, and then the coverage factor that is based on the confidence level scales the final result. So it may not necessarily be a standard deviation that it is scaling. But in a simple uncertainty model, it can be a standard deviation.
So is there, can you maybe specify that by an example that?
Okay, so let's say we, let's say if we measure some quantity that we can assume has a normal distribution. Let's say we measure a number of repeated times, and then we can take the standard deviation and then scale it by the coverage factor. So this would be a simple example.
Okay, another issue, and I think that was a good finding, is you found that there is a correlation between the accuracy of the estimate and the line loading. Okay, I'm referring now to the real power, the active power. And you said that these differences in accuracy can be quite significant and changing over time. So can you explain that, maybe by a numerical example, how this dependency evolves with the line loading, the accuracy of the estimate?
Well, based on the analysis, I would conclude that this change in accuracy is dependent on the, I mean, when it is loading of the line, it is dependent on the accuracy of the current transformer. And the current transformer, its measurement error is also partly dependent on the value of current being measured. And in these cases, we can see that if the current transformer is operating closer to its rated value, that means measuring a larger current, it is more accurate. And this translates to smaller uncertainties and higher accuracy in certain estimates.
okay, I think this is a, for practical viewpoint, a very good observation, especially from the viewpoint of how to move forward also. Okay, and if I'm looking now at your figure 2.4, I don't know whether you can put that up, that positive sequence resistance over time.
Sorry, I don't have these here.
Right, okay, but anyway, I mean...
Yes, okay, I'll...
I think, well, this is among the most interesting graphs, positive sequence resistance, positive sequence reactance over time.
Mm-hmm. Yes, 2.4.
So what is the... You have a huge interval there, uncertainty interval. Okay. It may seem like these are uncertainty intervals that cover, accuracies of, or errors of 100% and more. Is that correct?
Yes.
The question is then really, if you have errors of 100% and more, what's the value of that estimate?
Well, that's a good question, of course. I mean, it depends on the application in some sense, but of course, if you have errors of more than 100%, then the value itself, in most cases, does not have any value. But then I mean, of course, this in this case it is not very practical.
Okay, but the objective was to, I mean, at least when I come back to the beginning of your presentation, was about SCADA, EMS, and so on. Do they also have errors of 100%?
Well, hopefully they don't.
Hopefully they don't. So then of course the obvious next question is, I mean, these loss estimations that we have here, what value do they add?
Yes, but this depends on what quantity we're estimating, because the fact that the estimate of resistance has a very large value does not necessarily mean that measured values of other quantities have large errors. Because in the case of resistance, where the very large error comes from is that we're measuring the difference of two close values. So if at one end of the line you measure 100 plus minus 1, and at the other end you measure 100.1 plus minus 1, if you take their difference, you can see how it can have a very large error, even though the measured values at the ends themselves only have a 1% error. So that is the case with resistance, for example.
So what do we do with those values then? If does it have? I mean now specifically those resistance values.
Well, I mean, the monitoring of line resistance with the help of PMUs has been discussed quite a lot in literature, and these proposed applications of dynamic line rating based on that. And of course, for dynamic line rating, this value has no use, because you would need a very accurate measure of resistance to be able to get the sensible value of temperature. So in order to apply that, entire measurement system would have to be calibrated very well. Because if we don't have these systematic errors, we can get a more accurate estimate.
Well, but at least you have found that when the line loading is higher, the accuracy gets better.
It gets better, but not good.
Not good yet. So the question is then, of course, and you relate it to the current transformer, is there some trade-off between making the current transformer better, investing in more and getting a better estimate? Is there some, and a better estimate of the resistance then also, not only of the current? Do you see any use of that?
I think it would be easier to monitor the temperature of a conductor with some different technology, not PMUs. So I would, at least my opinion is that it would be easier and probably cheaper to monitor temperature of a conductor with another technology rather than try to achieve necessary accuracy in this measurement setup.
Because in your conclusion here you say, well, if more accurate estimates of line parameters are neither calibration or replacement of instrument transformers would be required.
If this was the goal, then yes.
If it was the goal, but you see, practically as of today.
Well, no, it depends because well, resistance is one of the parameters, but the uncertainties of other line parameters are smaller. And for example, the monitoring of coronal losses or the components of losses, both Joule and corona losses, is inherently still dependent on the same estimation principle. So it is also using the estimate of line parameters in calculating the loss component.
Okay, so these are a lot of practical issues, which I said, are certainly of value. So if you try to sum up from your experience, your in-depth analysis so far, what kind of parameters should be or could be within the next 5 years or with, reasonable reinvestment be well estimated by PMUs and which not?
Well, I mean, if we talk about these 4 parameters, the positive sequence, resistance, reactance, conductance, and susceptance, then I think for resistance it would be possible also to obtain results that are reasonable, but they wouldn't still be good enough for example, determining the temperature of the conductor. But the value of resistance itself, it could be, let's say, maybe a 10% error. So for like model validation or something, it would be suitable. And the other parameters, I think they can be estimated with accuracy that means that the values are usable. So
reactance.
Yeah. That's my personal opinion.
So Kai, do you have more questions?
No.
So we thank you for this. It's so we approach to another opponent. Vladimir, are you there?
Vladimir, can you hear us?
I can, yes, I can hear very well, and I'm full of the whole presentation. Maybe the question I didn't hear properly.
Okay, the floor is yours.
All right, good. Thank you. Well, honestly, I was not informed for how long we should inspire the candidate to report questions, but if I move back again to application of PMUs for example, thermal assessment of transmission line, because we can have issues which are related to overloading of transmission line, related to thermal processes. You know, the approach which you have is estimation of an average resistance across transmission line. Am I right?
Yes, that is correct.
Well, in this context, we might have a very hot part of transmission line somewhere on a fifth, for example, 55th kilometer or mile. But the average representation would not be appropriate for identifying such hot spots. Have you been thinking about that?
I completely agree with that. Of course.
So the point is that we should be aware about the application, about limitations, but as a matter of fact, phasor measurement units can really help when it comes to model validation from different aspects, but also from transmission line and network parameter estimation using real data. Also, a question very formal, of formal nature. When you say ambient data, what do you mean?
Well, in this context, when I say ambient data, it is. Sorry. It is measurement data from normal operating conditions, when we would generally assume that the system is in steady state, but we have small normal variations all the time.
Can you give me one example of ambient data? Just one variable, just physical variable. Which one it is?
Well, for example, the frequency.
Sorry, I didn't hear. Say again. For example.
For example, a measured frequency.
Okay, good. Ambient data, good. Ambient, it's not clear. I'm not using this terminology when you say ambient data. It was not very precisely defined in your thesis. I thought it may be pressure of air. But pressure of air might have to do with corona, because corona is a process, a visible process, which has to do with maybe with this ambient temperature, humidity, and these aspects which have to do with the weather conditions around surrounding conductors of transmission line. Good. So I would like to ask you just a question related to, again, to swing equation. So I know in your thesis you didn't put units, what means frequency in hertz, H in second. But active power, I believe that is in watts or kilowatts. Do you remember this? It's swing equation, I think it is 4.1. I would like that you check what open literature Prabha Kundur is saying and what your equation is saying. I mean, this is, my question has to do also with my contacts with GE, General Electric.
Yeah.
And the way how they see this swing equation. I mean, the way how they see this equation is more practical than that it is in textbooks. In textbooks, this active power is in per unit. But who in industry is talking in per unit? Sometimes. But when it comes to power, it's power. It must be mega, it must be giga. so that in your equation, I think it is in absolute values. And then I think that is the cause of this second square. But please just double check that. I don't want to speculate. I made one assessment very quickly when I had to do something, go through a few equations. Please double check that. I know that megawatt second square has been accepted from IEEE tough reviewers, transactions. So it made me very happy. So, but I still have some concerns, and I'd like to have this somehow explanation where it comes. I'm not insisting now, but because it's a little bit mathematical thing.
No, I can comment. I can comment now because I have the equation here, and yes, you're correct.
I see.
The power is in absolute values, but there is also the rated power component in the equation. So the equation 4.1, so we have the rate of change of frequency on the left, which has units of 1 per second squared, as it is hertz per second. And on the right-hand side, we have the power deviation and the rated power, so that this unit is cancelled out. And then we have the inertia constant in seconds and frequency, so we can get again hertz per second. And yes, because rate of change of frequency here is not in per unit, it is 1 per second squared, then if we take the effective inertia as the proportionality between the change in power, or the size of disturbance, and the rate of change of frequency, then the units turn out to be megawatt second squared.
Good, fine. It is consistent. It is consistent. But it's, again, when you talk to people from utilities, what is inertia? They traditionally say it is gigawatt second. And then suddenly second square. So this, if you explain that additionally, again, we talk about inertia, and before we talk about inertia, we should firstly define that. Again, I teach students and I talk about inertia constant, but it's proportional to kinetic energy. But essentially, the fundamental rotational inertia, it is coming from J. It is moment of inertia, but we talk about effective inertia, what I fully agree with you. This is a paradigm shift in our thinking now. We talk about effective inertia, which is seen through formula 4.3, and this is a very nice thing. Because this imbalance delta P can come from inertia response, can come from load, can come from synthetic inertia. But let me just point out formula 4.2. So in your question is, what is inertia? But in formula 4.2, you measure rate of frequency of equivalent inertia center. Or am I right?
Yes.
Good. And this, interestingly, this equivalent inertia center, to calculate it, you see, you have a couple of inertia constants inside. You agree?
Yes.
What means that to calculate effective inertia in your approach, which I honestly like, you have to know inertia constants of generating units or things which are inside the area. Am I right?
Well, yes, but if you look at equation 4.4, that is the practical implementation of it, where the center of inertia or the area frequency is calculated as a weighted average of local frequencies. And these weights are based on approximate knowledge about what the inertia constants would be like. So we don't have to know the exact values, but a general idea.
Yes, I agree with you with these weights, but if we ask, if a student asks you, what are these weights? Then you return back to formula 4.2, and then you say these weights have to be inertias. Am I right?
Well,
Not that.
to comment then in practice, I have assigned these weights more or less based on what the power of the generating units online near this node would on average be. Like I said, it is an approximate value of that, but it doesn't have to be very correct or very accurate.
So, all right, good. So, one more question. When you talk about area inertia, what is the area? How do you define an area?
Well, it is a set of nodes in the network that are connected to each other and separated from the rest of the system by a predefined boundary. So, which in practice, I would say it is a cluster of nodes that have similar frequencies.
Oh, yes, good. So I fully agree with you, although this hasn't been articulated in your thesis. In principle, I think that, I just want your opinion, we can quite in arbitrarily manner define what an area is, even go to the even marginal case that we say the area is a single generator. But we do that in a sensible manner. We say, for example, Scotland versus England. Actually, we use this coherency analysis and define through coherency analysis coherent group of generators, which could be one area. But this is something what has to do with coherency analysis. But I think that we could go to the even extreme proposal that area is that what we define as an area. And then the whole theory, the whole approach should also work for any area which we define. So area has input power, it has output power, we calculate input output, this is delta P, we calculate that using PMUs, it works. And then the question is this rate of frequency change, which one it is inside? For example, what if you in this area have no single generator, no single H? Can you just discuss this very interesting case?
Yes, that is a very interesting case, of course. Well, I haven't analyzed a case like that, so I can only speculate. But I think in practice,
it's complicated. The answer is because it's complicated because you are dividing something by zero, but actually the surrounding world has inertia.
Yes,
so,
exactly.
So in this context, it is very interesting. I mean, we are still struggling to define what is what. I work in SIGRE working group B5C4.61. It is impact of high penetration of renewables on system inertia. No, impact on power system protection. And it has to do also with frequency protection, under frequency load shedding. Then we are dealing with the system inertia and so on. So we still need to define some things. For example, what is actually my question about? How do you define area? And is your theory fully compatible with, for example, area without single generator? So these things are quite interesting. You can eventually put few words in your thesis about that, just to address them, eventually to think about that, eventually put few words more, few sentences more. if you just have time for this. And so by this, I would like to give Kaur word that you give a conclusion of my questions, and then it would be from my side at the moment.
Okay, thank you.
You're welcome.
Okay, thank you from my side as well. So we have covered the discussion with the opponents. So it's time for our local audience, and first we start with the Commission. I think we'd start with this end. So. Mati, kas on küsimusi? Okay, no questions. Indrek?
Yes, some questions, but I'm not specialist of this area, so don't be too stressed. The questions will be easier, I think. But nevertheless, I think as much as I see, there are two problems. One is that we are lacking of accurate and fast measurement methods to measure inertia. And the second problem is what to do then next, how to compensate load disbalance and frequency shift quickly. If we have this measurement data, then we should do something quickly. Can you comment which problem is bigger and more important?
Which of what?
Of those two, measurement,
monitoring or control?
Monitoring or then taking some actions.
Of course, it is most important to maintain system stability, maintain frequency in its limits. And of course, if these conventional means, synchronous generators become less common and there's less support from there, new controls are needed. And for that, different fast frequency response controls and services are being implemented and tested. And in some cases, these controls also operate based on knowing the value of inertia. So it is a contribution to that. But for example, in the Icelandic power system that I also studied in this work, there are some services. Some are simpler, some are more complicated. For example, there are certain industrial loads, aluminium smelters, that can ramp their power or their load either up or down for a short period of time, and they can do it quickly. And so in case of large disturbances, these controls are actuated, and the loads themselves help in maintaining frequency, or at least stopping the first swing in the frequency. But they are also implementing more complicated controls which are based on this wide area monitoring system, so that they also consider where in the system the disturbance is. Because as we discussed it as a two-area system, it is two areas that are quite weakly coupled, so that if you have a disturbance in one area, you don't want the response to come from the other, but you want the response to be local. So they also use wide area measurements to determine when and where to actuate the fast frequency control. And based on a measured value of inertia, they determine the size of it.
Mm-hmm. Okay, thanks. In short, I understand both problems are very important, including your PhD thesis is very important and state of the art, and it needs to be dealt. But further, how do you see this? What you have done here in the book? What is the potential of those methods? Can there be some kind of product? Can you develop from this some kind of product, some kind of software which you can sell, and or what do you think?
Well, I don't think I personally am going to develop these tools. But for example, with the case of inertia, I would say that biggest contribution was to show that this can indeed be done. We can monitor these small variations and calculate inertia. And after showing that, it is possible for vendors to develop such tools. And also, as a part of this Migrate project, there is a development of an inertia monitoring tool that initially was disturbance-based, but is now shifting also to continuous monitoring.
And how much work there is, do you think? How much you have done and how much is missing till we have a complete software that you can install somewhere in the distribution observing system? And
well,
is it a small step or a rather big step?
GE is already kind of advertising it as a solution, so I think they want to do it. Yeah, but it is not exactly the same method, but it's a slightly different implementation. But yes, it was initially based on disturbances, but now also going to work on continuous data. So I would say my role was to show that this can be done.
Okay.
And in the sorry, do you want to
finish?
So this was one part of the work, and well, in terms of transmission losses, I think there is potential to develop these forecast models for corona losses, as they are quite difficult to forecast, and if we can gather large amounts of monitoring data, it is hopefully possible to train better forecast models.
What about the forecast of inertia?
Yes.
Decreasing inertia, if you can measure very accurately and fastly the inertia in current state of time, it would be very nice to have already some kind of idea what is going to happen in maybe 10 minutes, in half an hour time. Have you considered this?
This is also already being implemented. It is based on, yes, monitoring inertia and some other parameters, like, well, as most of the inertia still comes from synchronous generation, then one of the inputs is the generators that are online, the inertial response from there, and then some other parameters that I can't remember exactly, but basically, yes, it is being worked on also in the same project, the Migrate project, forecast of inertia as well.
What to think about the future of DC distribution? This would solve all the problems what we are discussing here.
Of course, and if there's a DC grid, then there's no inertia in this sense.
Is it coming or not? What do you think? Are you a little bit informed about this?
Well, I think in some places it will appear, of course, but I don't know how long it will take and how fast it will spread. But,
okay, and you said that you showed future plans, how to move on. Are you working at university right now, and what do you plan to do next? Keep on research here at the university?
For now, yes.
Oh,
I
nice.
had some plans.
That's nice, always. Okay, let's move on.
Okay.
Thanks.
No further questions.
Good or bad? So
I got already answers.
okay, let's move on.
I have
Good.
some of them. Let's go back to this famous slide 15.
I'll take one with the same figure.
Yeah. Here we have some solid lines and then some sort of regions with different colors. Now I understand, please correct me if I'm wrong, but I understand that the monitored or measured value, these are the lines.
Yes.
But what show this area colored differently? What kind of information I can get from this additionally?
It means that, yes, the solid line is the measured value, but it includes some systematic errors, and this region or interval shows where the actual correct value should be with at the level of confidence. So even though this is our measured value, it could be either here or here.
But if you measure or monitor and you say that you get the solid line and then you say that there is some sort of error, though the error must be somehow defined. So if I look this picture, I'm a little bit confused. Maybe it comes from me. I agree fully that this is something new for me, that to show this way that in the area some sort of, and line is a measured value, but this measured value has errors, and then it could be in the same place.
Yes.
Different compared to this what you monitor.
Yes. But, well, I mean, the errors that cause this, of course, they have some values, but these errors are propagated from measurements of currents and voltages to these calculated values of losses.
Okay. Might be I am fool, but I still do not understand it, how it is possible, but anyway, let it be. But going forward, the blue one is a corona losses. Compared to this Joule region, why you measure your monitor it at all? Because you have only certain places this is a critical. And now my question is coming. What does it mean physically that there is a jump and after that nothing and before that nothing? Why this jump is coming?
Because
what is behind of this?
Because the conditions that enable corona discharge to take place on the conductor, well, in this case appear and here disappear, because it is largely dependent on weather conditions. So when
it comes once and then after that probably happen nothing, yeah?
Well, yeah, I mean,
and you can't predict it. So it is a very uncertain.
I would assume that it is possible to predict it based on these same weather conditions, but it is not very simple to do that
so
because
uncertainty is in this direction for the corona, not in this direction.
Well, in a way, yes, but in the measured value of losses, it is still in this way. When we start to forecast it, then it would be in this way. But this is not forecast here.
Okay, but now if we look the uncertainty, then for the corona it's relatively small, for the Joule it's relatively large. What kind of physics or what kind of mechanism behind of this that the Joule has much larger uncertainty compared to corona?
If we go back to the beginning here, when we analyze the transmission line in terms of the model, then Joule losses are losses that are anticipated in the resistance of the conductors. And well, in principle, if we can measure one accurately, we can measure the other accurately. That means if we could measure resistance accurately, our measurements of Joule losses would be accurate. But because resistance has by itself large uncertainty and large errors, then also Joule losses would have to have a rather large uncertainty because they are related to the same element of the model of the transmission line. Even though the errors in Joule losses are not as large as in resistances, because it also depends on some other things, and how the measurement errors are propagated into the estimates.
Okay. Now let it be this 115 slide in peace. You use in your dissertation, I just take a look, the figure 4.2, 4.3, 4.5, that they are models. Now, in my opinion, they are some sort of block schemes. And after that, you said that we use black box model. How it comes together?
Well, these block diagrams are used to explain the general idea of what kind of a system we're looking at.
Mm-hmm.
And when we're identifying the models themselves, they don't have the same structure. So these are only explanatory, basically.
So you practically do not know exactly what's happening inside. You look only the
inputs, outputs.
Input, output, and then try to justify the measured or monitored curves with some sort of polynomials or whatever other mathematical possibilities to fit the curves or match the curves.
Yes, basically yes.
Mm-hmm. Okay, and finally, every nice dissertation must have some claims. Can you rank your 3 most important claims? You put here contribution and whatever you call, but please name.
So as already discussed, I would say one of them is
3 most important.
One of them is to demonstrate that we can use continuous measurement data from normal operating conditions to calculate the value of inertia or effective inertia. Then the second is that we can, if we monitor a transmission line with PMUs, we can calculate transmission losses as separate components, which means that we can monitor them separately, and we can gather monitoring data about corona losses. And third would be to demonstrate how these principles of uncertainty analysis can be used to analyze such monitoring applications as the transmission line monitoring in this case. How we can analyze how the accuracy of measured signals affect the results, basically.
Good. The member of commission rests now.
Thank you.
I was just wondering who asked those questions. You completed the important part. So, Hannes?
Maybe just one question, because you already have so many grueling questions. So, from my side, just a quick look into the economical side. So, what do you think regarding you're mentioning page 41, then Estonian DSO Elering already has annual budget around 90 million euros per single year, fiscal year. So, and the cost of of loss of energy is around 10 to 50 millions. It's quite large version. What do you think? What is the actual number? What can be achieved when properly implement those new things that you are covered in your work, and also those deep learning and better forecasting, etc.
Well,
where is the actual point of where
yes.
you don't have to invest more or just leave it as it is?
Well, in general, we can't really decrease transmission losses with the help of any of that, but we can decrease some of the expenses on the losses, because, as I said, the energy consumed as losses has to be procured, and so it has to be known in advance and forecasted in order to do that. But if there are significant errors in the forecast, then there will be an imbalance in loss energy. And this causes extra expenses in order then to balance it out. This is a lot more expensive than buying them beforehand with the help of a good forecast. So if we can obtain good forecast models, we can reduce these expenses.
But how many percentage points, what do you think?
Well, I would say like even 1% would be pretty good. That would be like in hundreds of thousands of euros.
Yeah, but
well, for a small
but
system.
if you talk
like
about
Estonia.
deep learning and better forecasting, then it's
Well, but this is only the example of Estonia. If we take the entire, let's say, even the Nordic countries, where these amounts are a lot larger, so the total sums would be also a lot larger, because Sweden, Norway, Finland, they have long lines from north to south, and they have a lot of very favorable conditions for corona losses to appear. And so this
picture, what you showed us, also was taken in some
that's
Scandinavia?
That's from Canada.
Canada. Okay, then no further questions.
Thank you for the audience. I only have one question from myself. You mentioned that you have done 4-month research on some topic and used 2 creeds as an example, and you mentioned that you would like to investigate other creeds as well. So my question is, how bulletproof are your approaches? So if we try to go to another network, how much work we have to do in the country? So what is that constants that are like fixed, and what are the things that you have to restudy?
Well, if we talk about transmission losses, then this is quite simple to transfer from line to line. I mean, the basic equations are exactly the same. So it is mostly a matter of then analyzing also, the uncertainties or the results that we get, and then fixing these systematic errors. But in the case of monitoring inertia, this has to be set up a bit more like system specific. But I mean, it wouldn't necessarily have to be a very large amount of work, because after I finished the thesis, I made a quick study on some measurement data from Scotland, and it was possible to reconfigure it to Scotland and the GB system. So it is transferable.
Okay, so it is like 4th claim. I thank you. And now is the audience. Is there anybody in the audience who would like to ask something? Anything? Something new? Asked to repeat something? Found some mistakes on the page? Or Or anything else about the slide 15? No, then supervisor seems to be occupied, but do you have something to say?
Hello, everybody. From supervisor side and one smaller person also has an opinion. So, but let's try to keep it simple. I think today's discussion was a really good one, and Kaur work was, in my opinion, very interesting. The results showed, as the PhD thesis should show, new approaches and thorough discussion. Myself, it's from the historical point of view, it's quite interesting that Kaur came back. So it's his master was finished in KTH about totally different topic about nuclear energy, and now we are back in power systems. So in this sense, I think Kaur has showed ability to tackle different sorts of academic problems. We are quite fortunate that during this time that Kaur has worked, as his work has been very important part of two major projects that we have had in the department. One of the cooperation with the TSO in Estonia, and the other one is Migrate, that the one that's actually right now even continuing, and Kaur, his work is also continuing in that project. So he's been quite new challenges ahead, and I think Kaur has done a remarkable work. I think we are not holding up this discussion to so many minutes. So I think Kaur is definitely showed, from my perspective, a remarkable approach and ways to solve issues that are in front of us. So I really support Kaur in his work and hope we can continue to tackle the new issues that we brought up in the Kaur brought up in the presentation. And so thank you from my side also. Silence. Yeah.
Silent agreement. So I thank you for the presentation, for this fruitful discussion. And this is the point where we close this part, where the committee will gather for voting. I ask everybody else to leave the room, and we will invite you back in, so when we have done the voting. So thank you, and see you soon. Sorry, I will repeat what I just talked.